All right, welcome back. So today we're diving right into the mechanical heart of any modern machine shop.
We are.
We're talking about the CNC lathe.
Yeah.
And for anyone, investing in new equipment or just curious about where power meets precision, we're tackling the big one.
The spindle mechanism.
Exactly. The spindle mechanism.
And this is one of those decisions that it really lives on the balance sheet, not just on the blueprint.
What do you mean by that?
Well, if you choose the wrong spindle type, you could be looking at stalled cuts, bad finishes, and, really high scrap rates.
And long-term repair bills, I imagine.
Astronomical.
Yeah.
So our deep dive today is, you could say, a shortcut to understanding that fundamental trade-off.
And the trade-off is pretty stark, isn't it? We're comparing belt-driven versus gearbox spindles.
That's it.
And the key thesis, really, right out of the gate, is about what you're optimizing for. Is it high-speed precision and low operating costs, or is it just sheer brute force torque?
Precisely. The belt-driven systems are, let's call them the minimalist champions. They're great for high-speed finishing, they run quiet, they're thermally stable.
Yeah.
But if your business needs that superior torque for heavy-duty cutting, especially on super alloys, the gearbox is it's indispensable. You get higher material removal, but you have to accept the costs.
Which is noise, heat, and a lot more maintenance.
A lot more.
Okay, let's unpack this then. We have to start with the mechanism, because how the power gets there really defines everything else.
Yeah.
So how does the motor's energy actually get to the spindle in a belt-driven system?
It's all about simplicity, really. The motor is linked to the spindle with a pulley system and a high-tension belt.
Like a poly V belt or something similar.
Exactly, or a synchronous timing belt. And the beauty of this design is that there are very, very few moving parts. That means smooth, quiet power transfer.
And I've heard the belt itself is more than just a power conduit. It's actually an engineering feature.
Absolutely. The belt acts as a natural mechanical damper, so it absorbs all those high-frequency vibrations coming from the motor.
And stops them from getting to the tooltip.
It stops them from getting to the tooltip and messing up your workpiece.
Which is fantastic for your surface finish.
Yeah.
But there has to be a trade-off in that elegance, right?
There is. Because power is transferred through tension and friction, there's a tiny bit of inherent elasticity in the belt itself.
So it's not a completely rigid connection.
It's just slightly less positive than a solid mechanical gear train.
Okay, so let's jump to that gear train, the gearbox or the geared head system.
Yeah.
When we talk about rigidity, this is the polar opposite.
It's a completely different league. We're talking about a complex mechanical assembly, all inside an enclosed oil-filled headstock.
Right.
And inside, you have multiple sets of precisely machined helical or spur gears. Power transfer is direct. Metal-to-metal meshing.
And this is how they get that torque multiplication.
Correct. By changing the gear ratio, the operator engages different combinations of gears. Usually there are 2 to 4 speed ranges, and that gives you a massive mechanical advantage.
But all that meshing has a downside. You lose some efficiency.
You do. We're looking at a typical efficiency loss of around, say, 5 to 10%.
And that's not just wasted power, is it? It's generating other problems.
It is. That lost energy has to go somewhere.
Yeah.
It becomes friction. And crucially, it's the energy needed for something engineers call oil churning.
Oil churning. Okay, for those of us not neck deep in gear mechanisms, what exactly is that?
Think of the gearbox like a blender filled with thick oil.
Yeah.
The gears are just constantly spinning and splashing through that heavy fluid. That drag, that resistance, is oil churning. It generates heat and consumes power before you even take a cut.
Okay, this is where it gets really interesting, especially for shops working with difficult materials.
Mm.
Let's talk torque.
Yes.
If you're cutting a huge billet of something nasty, you need immense rotational force just to stop the spindle from stalling.
Absolutely. And this is the one area where the gearbox just reigns supreme. That gear reduction system is basically a massive torque multiplier.
So you trade speed for power.
The operator shifts into a low-speed gear range, sacrifices thousands of RPMs, and in return gets raw, brutal power.
What kind of multiplier are we talking about here? Is it significant?
Oh, it's huge. If you look at the torque curves, at speeds below 1,000 RPM, which you often need for hard materials, a gearbox can generate 2 to 4 times more torque than a comparable belt-driven system.
You mentioned tough materials. Why is that combination of low RPM and high torque a necessity for something like, say, Inconel?
That's a critical question. Inconel is a super alloy, right? Used in jet engines.
Right.
And it has two terrible properties for machining. It resists heat and it work hardens
So
instantly.
if you cut it too fast, it gets harder.
Exactly. If your cutting speed is too high or your feed rate is too low, the material hardens right under the tool. So you have to cut slowly but very aggressively.
You have to take a deep, continuous cut.
A deep, heavy cut to get under that hardened layer and just power through the metal. And that takes immense, continuous rotational force. It's the only way to get high material removal rates, or MRR.
And if you can't hit high MRR.
Your cycle times explode, and you lose money. It's that simple.
So for industries like aerospace, oil and gas, heavy equipment, the gearbox isn't a luxury. It's the only way to get the job done efficiently.
It is the only practical way. On the other hand, with the belt drive, the torque is tied to the motor's power and a fixed pulley ratio.
So the torque drops off at low RPMs.
It drops off fast. And under extreme load, that belt can actually slip on the pulley.
And then you lose all your power.
You lose effective power, and you can stall the cut completely.
Okay, let's shift focus to the operational environment. What's it actually like on the shop floor? What are the big differences in, say, noise and thermal stability?
Oh, the differences are profound.
Yeah.
And they directly affect part quality and, frankly, worker health. Belt-driven systems are much, much quieter.
How quiet are we talking?
Often running below 70 decibels. For context, that's like a busy restaurant.
And the gearbox.
The gearbox, with all that heavy-duty metal-on-metal meshing, is inherently louder. Under a heavy load, you could be pushing 80, even 90 decibels.
That's the difference between having a conversation and standing next to a jackhammer.
It is. It requires mandatory hearing protection. It's a major factor in shop fatigue.
And the thermal side of things is just as important for precision, isn't it?
I'd say it's maybe more important for your scrap rate. The belt drive generates way less internal friction and heat.
Plus, the motor isn't sitting right on the headstock.
Exactly. The motor's heat is physically isolated by the belt gap, and all of that promotes better thermal stability.
So why does thermal stability matter so much to the listener who's focused on the bottom line?
Because accuracy is tied directly to temperature. If the machine structure heats up, the metal expands.
And your tolerances go out the window.
The accuracy you set at the start of a 10-hour cycle is gone by hour 5. If you're working with tight tolerances on expensive materials like titanium, thermal instability means you're scrapping thousands of dollars.
Whereas the gearbox is just actively generating heat from all that friction and oil churning.
It's fighting itself constantly. To maintain any kind of precision, gearbox spindles almost always need an oil cooler to actively pull heat out of the headstock.
Which is another component to buy, power, maintain, and
Potentially fail.
Right. And we can't forget vibration. That gear meshing has to be transmitting vibration straight into the machine frame.
It does. The rigidity that gives you torque is a curse for vibration control. Unlike the belt, which acts like a shock absorber, the gears transmit everything.
Which is why, for a mirror-like surface finish, the belt drive usually wins.
Hands down.
Okay, that brings us to the long-term investment, total cost of ownership. What do these mechanical differences mean for maintenance and uptime?
This is where the belt drive's simplicity really translates into huge financial savings. And the most compelling part of it, I think, is the concept of the mechanical fuse.
A fuse? Okay, tell me more about that. How does the machine protect itself?
Well, in the event of a crash, and let's be honest, every shop has one eventually.
It's inevitable.
The belt is designed to be the weak link. It will often slip dramatically, or it will just break.
So it's a deliberate, inexpensive failure.
Exactly. Replacing a belt is a quick job. You can do it in-house. It costs maybe a few $100s. But crucially, that broken belt just protected the really expensive stuff.
The motor windings, the spindle bearings.
The multi-$1,000 components are shielded from the full impact of the crash.
That makes perfect sense for risk management. Routine maintenance must be simple, too.
It is. You check the tension, you replace the belt every 2,000 to 5,000 hours. Minimal downtime.
Okay, now contrast that with the geared head system.
Gearbox maintenance is significantly more demanding. It's specialized work. You have regular oil changes, oil analysis, and periodic inspection of gear wear and something called backlash.
Backlash, let's define that one quickly.
Backlash is essentially the slop in the gears. If you reverse the spindle direction, it's the tiny delay before the gear teeth re-engage.
And as the gears wear, that slop gets bigger.
It gets bigger, and that kills your precision in things like threading or tapping. Monitoring and correcting that requires a skilled technician.
And if a component actually fails, A chipped gear tube.
If a gear or a bearing fails, you are looking at a major, complex rebuild of the entire headstock. That means significant downtime weeks sometimes and repair costs that easily run into five figures.
And crash protection.
It's poor. That rigid connection means that during a crash, the full impact force goes directly through the drivetrain. There is no fuse.
The force goes straight into the gears.
Straight into the gears and the spindle bearings. The rigidity that's its greatest asset for cutting becomes its greatest liability in an accident.
So let's wrap this up. What does this all mean for the listener who's trying to spec out their next machine? The final decision framework seems pretty clear.
It is. If your shop is focused on high volume, you're using standard materials like aluminum or mild steel.
Or if you need the absolute highest surface finish possible.
Right. Or if low long-term operational costs are your main priority, you choose the belt drive. You're optimizing for speed, precision, and simplicity.
Right.
But if you are cutting large diameters, doing deep, aggressive roughing, or dealing with the toughest materials out there, titanium, Inconel, where you just need raw mechanical torque,
Then the gearbox is non-negotiable.
you have to choose the gearbox.
Yeah.
You're optimizing for brute power, and you accept the noise, the heat, and the complexity that comes with it.
Which leads to a final thought for everyone to chew on.
It does. A final provocative thought for you to consider. Given that gearbox spindles gain their advantage from brute mechanical force, but then require all this complex engineering oil coolers, heavy construction, sophisticated lubrication, just to manage the heat, noise, and friction they create. How does all that added complexity ultimately challenge the overall long-term efficiency and reliability when you compare it to the inherent elegant simplicity of the belt drive? Something to ponder the next time you're looking at a quote for a new machine.